Okay, sorry about that little pause in the action. Hopefully, oh, you took an opportunity and stretched and took a little lap around the room or whatever you needed to do so that we can finish this out. There's only 3 more operations. They should go fairly quickly, but I knew we wouldn't be able to get there. So here we are. Week 14, day 1, video 2. We'll wrap this up, and then day 2 material will actually be not nearly as long as all of this vocabulary stuff, definitions, properties, making sure we're all on the same page, we all have the same knowledge. So the next set is closure. Okay, and it starts out the same as the others. It says, given a set and an operation, the solution is also in the original set. Okay, so what the heck does that look like? Get that out of the way, sorry. Here's my example. Okay, we have something with some kind of an operation. Let's make it a question mark operation, and it's equal to something else. And what we would say is all of these are in the given set. Okay, that's the way that would work. So you're given 2 numbers that are in the original set. You do whatever operation this is. We don't know what operation it is. Excuse me, and when we're finished, we'll have a number that was actually in the same original given set. If it's not, if we get some other number, then that throws us out of our set. We are not, then whatever operation we're doing is not closed, okay, in that particular set of numbers. So here's an example. We'll say, my question is the operation of multiplication closed, that's what they call it, closed for closure, is it closed on the set of whole numbers? We're sticking with whole numbers. We started out with those, so we might as well go on through. Okay, so is the set of, is the operation of multiplication closed on that set of whole numbers? So what that means is you're going to give me 2 numbers. We're going to multiply. That's what we said we were going to do. So a whole number times a whole number, and we better end up with a whole number. So the trick is 2 whole numbers. We're going to multiply them, and this is also a whole number. That's what it means to have the property of closure in there. Okay, so my example is a 5 and a 10. 5 times 10 would give me 50. And I say to myself, are 5 and 10 both whole numbers? I better start with whole numbers because that was the set I was given. The answer is yes. And is my answer or my solution here also a whole number? And the answer is yes. So that's working for me. So I feel like I'm doing a pretty good job here with the closure. And then I think, what could throw me off? Well, I'm in whole numbers. So 0 could throw me off, right? He's always a problem. So we're always going to worry about him. So what if it had been 5 times 0? Multiplying those guys together. Well, those are both whole numbers, so that would equal 0, right? Is that still a whole number? Well, yeah, if he was a whole number here, he's a whole number here, right? So that's okay. So does it matter that I multiply something by 0? No, I'm still getting a whole number. Is there anything that I can do to 2 whole numbers when I'm multiplying that would kick me out of whole numbers and maybe suddenly I get a fraction or suddenly I get a negative number or something like that? And the answer is no, it doesn't work that way. So here, when I say is the operation of multiplication closed on the set of whole numbers, the answer is absolutely yes. Okay, so I'm going to take just a second here because right here's my example. Because I want to make sure that we know what it looks like if it wasn't. So here's my next question. Is the operation of subtraction. Oh, no, let's do division. We haven't done division yet. Is the operation of division. It would have worked on either one of them, but closed on the set of whole numbers. So what I'm telling you is the answer is no to this one because it's going to kick me out. But it would have worked for subtraction also. We would have had a problem with subtraction. So here I'm going to do division, something divided by something. I want both of those somethings to be whole numbers. And hopefully when I'm done, I get a whole number. Now we could be a little bit, I don't know, I guess oblivious or not really searching for the pattern is what I'm thinking. And we could pick some numbers that aren't going to, or that might work here okay. So let me just do the opposite of this one. 50 divided by 10 gives me a 5, right? That one's okay. 50 and 10 are both whole numbers. 5 is a whole number. All of those are whole numbers. So if I'm being a little, I don't know, obtuse or oblivious or just not searching, not really looking for the counterexample and go, oh, it works. And you would be wrong because it doesn't work. So this is a really great example of when you need to look for that counterexample. So I'm thinking to myself, when could I possibly do some kind of division problem and I'd be working with whole numbers and it would throw me out. So literally I'm just going to flip these two. Okay, I'm going to do 10 divided by 50. Those two are still whole numbers, right? 10 divided by 50. That would give me 10 over 50, or 1/5. And when I look at that guy, 1/5, so this is a whole number. This is a whole number. I'm supposed to be working in the set of whole numbers, and I'm looking for closure, so I want my answer to also be a whole number, but what about this guy? Is that a whole number, 1/5 or 10/50? Nope, that's a rational number, right? So that's what I mean by it kicked me out of the set, basically. By doing this operation, when I do this legitimately, I actually do the division, my answer is no longer a whole number. So here, when I find a counterexample, and there are lots of them once you think about that, okay, what throws me into fractions? Well, that did, but there's lots of other stuff. 10 divided by 30 would be 1/3, and 2 divided by 3 would be 2/3, and whatever. So there's lots of examples of when this doesn't work once you know what you're looking for, right? So you're looking for some division that ends up with a rational number, a fraction. Okay, so is the operation of division closed on the set of whole numbers? No. Okay, so your process will be to try to find when those things don't work, okay? And I'm going to ask you some very specific questions, like this one, is the operation of division closed on the set of whole numbers? And you're going to have to tell me no and give me a reason. So your reason can be a counterexample. If you got a great counterexample, just give me a great counterexample, that's fine. But you've got to know why it does or does not work, so... And does not work is actually easier because you got that counterexample coming in. Okay. So, yeah, addition and multiplication are both closed operations on the set of whole numbers, but subtraction and division are both not closed. Okay, so here's my question. I want you to try on your own. Will subtraction be closed on the set of integers? Okay, so the set of integers, we just said it's not closed on whole numbers, right? So now we're wondering, what about integers? So hopefully you can kind of think about some possible examples, right? So think about examples. So start out with the obvious ones. For instance, 3 minus 2. The operation is minus in the middle here, right? Because I'm subtracting. That's a 1. 3 minus 2, those are both integers. 1 is an integer. Okay, those all work, no problem. But we can't just stick with that, right? We have to think about what are the special cases. So what about if I flip those around, 2 minus 3? Okay, when we were dealing with whole numbers, this would have given me a -1, and that would have kicked me out of whole numbers, but I'm not in whole numbers now. It's asking me about integers, right? So that's my set. So that's why I said you really have to pay attention to both the operation and the set that I'm working on. Well, in this case, -1 is my answer, my solution. It's also an integer, right? So that's okay. So it kicks me into integers, but I was already in integers. So then you might think about other stuff. Well, what if they're negative numbers? What if one of them's negative? What if both of them are negative? How about 5 minus -2, for instance? Well, 5 minus a negative becomes a positive. 5 plus 2 is a 7. Is that an integer? Yeah, that's okay. What if it was reversed? What if it was -2 minus 5? Okay, so the negative is the smaller number, it's at the beginning. What if the negative is the bigger number at the beginning? So you try all your different combinations, basically. Well, that'd be -2 minus 5 is a -7, right? That's okay. So you're just looking to see, is there anything weird that might happen to me here that might kick me out of integers? And the only weirdo I'm thinking at this point is, again, 0. But 0 is actually not going to be a problem either, so let's see it. What if I did 0 minus 2? Well, that's just what? -2, right? So that's still inside of integers, no problem. And if I reverse the order, 2 minus 0, who cares, right? That's just still a 2. So I'm okay. I'm okay. I'm not finding anything that is kicking me out of the set of integers, and that's because basically if you think about, let me see if I can find it. If you think about our sets here, like we've been doing whole numbers so far, right? But now we're out here in integers, so integers include the negatives. Sometimes something might not work in an integer, like division might not work with integers, but it might be closed in rationals. So sometimes you have to go a little bit further out on your rings, so to speak, inside of your nested subsets there. Okay, so we haven't answered the question. Is subtraction closed on integers? The answer is yes. And all results that we're picking are also in the set of integers, and we just can't find a counterexample. So it's very difficult to say we're absolutely correct, although I think I can convince you guys, but there is a set of classes devoted to like number theory and complex numbers and stuff like that are devoted to proving that things like this are indeed true. So you can go and work on some of those if you wanted to. Okay. All right, 2 more. Identity. Okay. Identity says that, and these two are both kind of related to each other. If you're given a set and an operation, a number is said to be the identity. A number is said to be the identity for that operation if, and it looks like this, A, and we're going to do smiley face here, E, is equal to E, smiley face A, is equal to A. Okay. So in other words, A is any element in your set, any number in your set. Smiley face here is my operation, so we'll fill that in with add, subtract, multiply, divide, whatever. And E is my identity element. Okay, and it shouldn't matter which way I do this, forwards or backwards. If I add or multiply or subtract or divide, and I've got this particular number in there, will I get back what I started with? So basically what they're saying is, you have some number in our thing, you do this whatever operation with the identity element, you get back that same number. So what I tell students sometimes is, think of identity like you're looking in the mirror and you see yourself and you know yourself, so you know what your identity is. So we take the A guy, we do all this stuff with it with the identity element, but it doesn't matter. It's just like looking at a mirror here and we get out the thing we started with. So an example, an example here could be if I'm working with addition, using addition. And for addition, you would have to at least start with the whole numbers in order to be able to do this, because starting with natural numbers, there's nothing that would work. So using addition with whole numbers. Again, something plus this guy gives me back the original item is what we're talking about. So let's say whole number, pick your favorite whole number. How about 15? Is there something that I could add to that and I would get back a 15? That's what we want to know. And hopefully the fact that I said using whole numbers instead of natural numbers might tip me off there a little bit, that what number is in whole numbers that's not in natural numbers? It's a 0, right? 15 plus 0 gives me back the 15. So it doesn't matter that I did this operation with this other number here, it gives me back the 15. By the way, what might happen with multiplication? Would the identity, or I'm sorry, would this work out with the identity number being 0? 15 times 0 gives me back a 15? No. So it doesn't work out that the same number is in all the operations. Multiplication actually has its own identity element. It's a 1, right? So we have this. So the answer here would be 0 is the identity element for addition. And actually what we see is it doesn't really matter which group I'm in as long as I'm not natural, because natural doesn't have 0, right? So I can use 0 in all those others as I go forward. Irrational, would it work for irrational? Yep, it would work for irrational. Imaginary, yep, it works in all of those sets. So 0 is just the identity element for addition. And 1's going to work similarly in multiplication. Okay, one more property, and we will be all done here for the day. So here we go, the inverse property. Okay, given a set and an operation. You should be tired of me saying that. I'm tired of saying that, so hopefully you're tired of hearing it. Given a set and an operation, a number is said to be an inverse of another number if, okay, we're going to use a little check mark here. A check mark B is equal to B check mark A, which just means the order doesn't matter, right? And I get back E, where E is the same guy we just talked about, the identity element, right? So this is my identity element. Okay, so this guy is any number in the set. The check mark is my operation. And the B here would be my inverse. Okay, and same thing here, just in the opposite order. So it's the inverse of A, right? Because it could be different numbers depending on what else we're doing. So let's get an example of that. We'll actually probably do 2 of these examples. Let's do for addition first. Addition of whole numbers. We'll just stick with what we've been doing. Okay, so find your favorite 2 whole numbers, or find your favorite whole number and say, what can I add to it? 5 is my favorite whole number right now. What can I add to it that will give me back my identity? Well, hang on a second, because we said that the identity for addition was the 0. 0 is the identity element for addition. So 5 plus something, and I'm going to get back a 0. So the question is, what the heck could I put in that box to get me back a 0? And the answer for addition is the inverse is going to be called the negative of whatever was there, right? Okay. So this was it's called the additive inverse. Okay. So that's if I was in whole numbers. What if I was in integers? Well, I would have started maybe with -5. Let me throw that over here. My starting number would have been -5. I'm still adding, because that's the operation I said. And I would want to add something to it that would give it 0. Well, what would I add to -5 to give it 0? Well, a 5, right? Okay. So this number would be the additive inverse for -5. That was the additive inverse for a +5, right? Okay, so it's interesting because what ends up happening is each and every single number ends up having its own additive inverse, right? If you told me, and it becomes pretty easy to see, now that we see all we're looking at is opposite operations on those, right? So the positive, his additive inverse is a negative, the negative guy, his additive inverse is a positive. It doesn't matter if it's a fraction or an irrational. I'm trying to get to 0, right? So I'm always going to think about your 0 pairs. I'm always going to 0 these things out and get back to here. So if I said 22 million, you would say, and I said, what's its inverse? You would say, -22 million gives me back the 0, right? If I said 5/4 and I wanted his additive inverse, you'd say -5/4. Gets me back to the 0. So it doesn't matter what I give you there, okay? The other example, because these are the only 2, by the way, that have identities and the only 2 that have inverses, is what about multiplication? Multiplication of whole numbers. What about that? So, all right, let's think about it. I've got a 5. I'm going to multiply it by something. And I want to get back the the identity element, but hang on a second. The identity element in multiplication, we said, isn't going to be 0, it's going to be a 1, right? So what am I going to multiply 5 by to get back to a 1? Well, in this case, it's a 1/5, right? This would be the multiplicative inverse for 5. And again, it's specific to that particular number. So the multiplicative inverse for 5 is 1/5. So that's what would get me back to the 1. That would be in whole numbers. Again, over here for the integers, if I started with a -3 and I want to multiply it by something to get me back to a 1, what would happen there? It's got to be 1/3, right? But it's also got to be negative. So here for multiplication, the sign actually stays the same for my inverse, but instead I'm flipping it, right, and making it into a fraction, or if it's already a fraction, I'll show you one of those in a second. It would just, it's just the reciprocal, right? It would just flip it upside down. So for rational numbers, let's say that we had 5/3 times something, get me back to the 1. What would I have to multiply 5/3 by in order to get a 1? Yeah, it would have to be a 3/5, right? So again, the reciprocal. So in the case of multiplication, the multiplicative inverse for whatever is always its reciprocal. Whether it's positive or negative doesn't matter. It just keeps the sign, and then we just flip it, right? Okay, so that is it, thank goodness, for all your sets and properties. This is a really long day, but day 2 is going to be a lot shorter. So hang in there, and we're almost done with the semester. Yay! See you guys soon.